Okay, so hey guys, so welcome to the third part of our lecture on vector spaces. Um, from what I've seen by looking at the notes, I think I'm going to do another one probably this weekend, but I'm not going to require you, or not even going to tell you to attend, or maybe if you want to. I think I'm going to do it on a Saturday or Sunday. Also, I believe you have seen your test scores, right, on a Blackboard, right? And also, if some of you have any complaints about the test and you feel like you deserve more, I'm willing to discuss. Uh, Also, I'm planning to do another video with discussing the problems from the test with the solutions and everything. So if you have, like I said, any questions, complaints, comments about the test, we're more than welcome to address them. Okay, so without being said, let me get started. We will, like I said, we will talk about today. We will continue our adventure on vector spaces, and in today's lecture, probably like I said, I'm not going to cover everything about the rank, nullity, and so on. Um, I will most likely dwell on spanning sets, linear independence, basis, and dimension. So I'm not going to go further than this. And probably the rank and nullity, well, we'll discuss it in another lecture. Okay, so let's get started. Remember that we have talked about so far about um, vector spaces. We have seen what is a subspace of a vector space. We have identified which one is a subspace, which is not a subspace, and we have seen an example of a subset which was not a subspace. And the simplest example you can think of is the set of integers, right? And now, and also we have seen another example, this one here, right? A subset of R2, which is not a subspace. You see, it's the set of vectors with non-negative components. It's not a subset, a subspace. Okay, now we'll continue with spanning sets. And linear independence. We will see why this is important and why um, we'll see what kind of role they will play for vector spaces. But before we go and start talking about these, let me talk about the very first thing I want to talk about is um, linear combinations of vectors in a vector space. Okay. So what is a linear combination? So let's start with the definition. A vector V in a vector space V is a linear combination, of vectors, let's say U1, so I'm going to keep the notation from the notes, U1, U2, UK in V, where the vector V can be written as the following. So this can be written in the following. V is C1U1 plus C2U2 plus CKUK. Okay, so that's what we will call a linear combination of vectors in a vector space where we need to specify where C1, C2, CK are scalars. So that's the linear combination of vectors. Oh, okay. Now let's see. I always like to, when I do a theorem or a definition, I always like to provide some examples. So let's see examples. And let me start with the following example. Let's see the first one. Let's see, let me give you the set of vectors. For example, the set of vectors, let's say in R3. So I'm going to pick an example of vectors in R3, a set of vectors. Let's say as to be the first vector, let's say 1, 3, 1, 0, 1, 2. And the third one, let's say it's 1, 0, and -5. Okay, so this is the vector. The question is, let's denote the first one by V1. This is V2, and this is V3. Now the question is that I want to ask is let's say V1 a linear combination of V2 and V3? That is the question. Is indeed this vector a linear combination of these two? The first one, P1? Well, let's go back to the definition. As you can see it here, we've said that V is a linear combination of vectors U1, UK if V can be written in this way, right? So you multiply the scalar by the first vector and you add, then you add it with the multiplication of another scalar with another vector and so on. So that is the question. What do you think? Do you think V1 is a linear combination of V2 and V3? Do you think you can find some scalars, let's say C2, C3, let's denote them like this, such that V1, so in other words, so let me translate this question. Can we find, let's say, alpha and beta, scalars, such that V1, we say that we claim that, well, we want to see if V1 can be written as alpha times V2 plus beta times V3. That is the question. What do you think? Oh my God, now it's even worse with the sun. It's it's fine. Okay. So what do you think? Do you think there exists an alpha beta such that V1 is alpha? Well, let's, for example, do you think V1 can be written as, let's say, if we take alpha to be 3 and beta to be 1? So can be this written as 3 times V2 plus 1 times V3? Well, the only thing you need to do is just to see Let's compute each one of them. So let's see, 3v2 plus 1 times v3 is nothing else than 3 times 0, 1, 2 plus 1 times 1, 0, negative 5. So this is a vector here. We have the multiplication of a scalar by a vector. So the first one will be 0, 3, 6 plus 1, 0, negative 5. And indeed, if you, will be 1, 3, and 1. This is nothing else than just what? The first vector. So indeed, this is what we call a linear combination of vectors. So in this case, you have seen that V1 can be expressed as a linear combination of the vectors V2 and V3. Okay, let me give you another example. So this is example number 1. 2, and in this case I'm going to take a set of 2 by 2 matrices. So the set of um, vectors in M22. Keep in mind that M22 is the set of all 2 by 2 real matrices. Keep in mind that. And the set I'm going to consider is the following. Let's say S is, and pay attention, the elements in this set are matrices. So that's what my vectors are. So let's say the first one is 0, 8, 2, 1. So this is V1. The second one will be 0, 2, 1, 0. That's V2. The third one, it will be negative 1, 3, 1, 2. So this is V3. And the last one is this matrix, negative 2, 0, 1, 3. And this is V4. Okay. So this is my set S. Now the question is, do you think you can find a vector that can be written as a linear combination of other vectors? That is the question I want to answer. So, well, let's see. Maybe I'm claiming, so the question is V1, let me be more specific. Is V1 a linear combination of the vectors V2, V3, and V4? That is the question. Well, the only thing we need to do is to find if, in other words, the question is, can we find scalars alpha, beta, gamma, and gamma, so real scalars, such that V1 is alpha V2 plus beta V3 plus gamma V4? That is the question. So I want to have this writing here. Can I do this? Well, you can do it. I'm just going to tell you directly what are the coefficients, and then we identify how we can, then I'll show you how we can find a linear combination. In other words, you can ask me, how the hell did you come up with those scalars, alpha, beta, and gamma? Like, where'd you get those scalars from? Well, I'm just going to tell you directly what these are. So alpha will be 1, beta is 2, and gamma is negative 1. Well, let's see. In other words, I'm claiming that V1 is V2 plus 2 V3 minus 1 minus V4. Let me minus V4. Well, let's see. Is this true? let's see, V1 is this matrix 0, 8, 2, 1. The V2 is 0, 2, 1, 0 plus 2 times this matrix V3, which is negative 1, 3, 1, 2, minus the fourth vector, which is given by this 0 to negative 2, 0, 1, 3. So that's it. So this is V2, this is V3, and this guy is V4. The only thing you need to do right now is just to look at the matrices, do the operations, and now let's see. Let's see this part here, if we want to do it. This will be, let's do it quickly, 0, 2, 1, 0 plus this guy is negative 2, 6, 2, 4 minus this guy, negative 2, 0, 1, and 3. And now if you do all the operations here, this will give us, the first one will be negative 0, then you'll have 8, then I'll have 3 minus 1, 2, and then the last one is 4 minus 3 is 1. Which is indeed this matrix right here. Haha. So V1 is a linear combination of vectors V2, V3, and V4. Okay, that's great. Now, the question is, as you can see in these two examples, I only provided a way. I told you what is the linear combination, but a legitimate question for you to ask is how to find a linear combination. Combination of vectors. That is the question I want to address. So, in other words, how do we find those those scalars alpha, beta, gamma, such that a vector can be expressed as a linear combination of other vectors? And the following example will address exactly this issue. So we want to find a linear combination. Let me give you an example. Write the vector W, let's say 1, 1, 1, as a linear combination, of vectors in the following set, in the set, and let's say this set S is given by, let's say 1, 2, 3. This is the first vector. Let's say this is V1. The second one will be 0, 1, 2. This is V2. And the third one is negative 1, 0, 1, V3. Okay, so pay attention. I want to write this vector here, W, as a linear combination. So W is a linear combination of vectors V1, V2, and V3. So this means what? What does it mean? So this means that we need to find scalars, let's say C1, C2, C3, such that this vector W, which is here, is C1 times V1 plus C2 times V2 plus C3 times V3. Okay. So this is, and now let's identify. So this relation right here, it will be equivalent with the following. So W is 111. This is C1 times V1 was 123 plus C2 times 012 plus C3 times negative 101. Okay, that's great. Now, guess what? You're going to do the basic operations with vectors that we have learned, and this will be equivalent with 111 equals, let's do it, C1, 2C1, 3C1, plus 0, C2, 2C2, plus negative C3, 0, and C3. Putting everything together right now, we will get the following. 111 is, and now let's add these vectors, will be C1 minus C3, 2C1 plus C2, and the last one will be 3C1 plus 2C2 plus C3. Now we equate, we have two vectors which are equal. Now the components, we must equate the components, and this will give us the following system. You see, at the end of the day, we end up with the system again. C1 minus C3 is 1. 2C1 plus C2 equals 1. And the last one is 3C1 plus 2C2 plus C3 equals 1. This is a system of linear equations you have you are already used with this. You can consider the augmented matrix. So the augmented matrix is given by what? Let's write it. 1, 0, negative 1, 1. 2, 1, 0, 1. 3, 2, 1, 1. And then at some point, and I'll leave it to you as an exercise, doing elementary transformations, I'll leave it to you as an exercise here, you will end up using, okay, Gauss-Jordan elimination. So you go all the way to the end. You will end up with the following matrix. So this will be equivalent with the following matrix, which is given by 1, 0, negative 1, 1, 0, 1, 2, negative 1, and the last one will be 0, 0, 0, 0. So you end up with a matrix which has a row of zeros. What do you think is going to happen to the system? Can you answer me this question? You can also be vocal about it. So what do you think is going to happen to the system of linear equations? To be more specific, how many solutions do you think this system will have? Liliana says infinitely many. Indeed. So this system has infinitely many solutions. And this is what we should keep in mind. So in other words, there are infinitely many ways of writing that vector as a linear combination of the other vectors. And the solutions are given by, so C1 will be, 1 plus t, C2 will be -1 minus 2t, and C3 will be t, where t is a real number. So we parameterize, let's say, C3 by t, and then we obtain that C1 and C2 in terms of t. So there are infinitely many ways of writing that vector W as a linear combination of vectors V1, V2, and V3. You can, let's parameterize, for example, let's take t equals 1. If we take t equals 1, we obtain a particular solution. We have C1, C2, C3 to be, let's say, 2, -3, and 1, right? And of course, we can write that our vector W as a linear combination of this, which is 2v1 minus 3v2 plus v3, 1 times v3. So this is just an example of a linear combination. But you can also take t equals 100. You have another linear combination. And in this way, you can exhibit infinitely many linear combinations of vectors. Okay. Now the question is, you've seen, you have seen vectors now that can be expressed as a linear combination of other vectors. But can I write any vector as a linear combination of other vectors? And I want to insist on this example that we just did. You have seen, let's go back to the statement of this example. You see, this says clearly that the vector W, which is 1, 1, 1, the components are all identical, 1, it can be expressed as a linear combination of V1, V2, V3. In fact, there are infinitely many linear combinations. But now the question is, if I take another vector, let's say, let's take another one. Instead of 1, 1, 1, let's take, for example, 1, -2, 2. Let's modify it just a little bit. And can we express, can we express this other vector as a linear combination of these vectors? So I want to answer the following question. Can we write any vector as a linear combination of other vectors? And the example I have in mind, or I would say the counterexample, the answer is no. I cannot write any vector as a linear combination of other vectors. And the example I have in mind, let's take this vector, 1, I said 1, -2, and 2. I want to write this. Cannot be, cannot be written as a linear combination, of vectors given in the previous example. So vectors, let's say v1, v2, and v3 from the above example. Okay. In other words, there is no way I can find C1, C2, C3 such that, so the question is, can we find C1, C2, C3? Well, we already answered the question, but because we've said that this cannot be written as a linear combination of vectors. But if this was true, well, let's justify this. In other words, this can be, this is equivalent with saying that W can be written as C1 times V1 plus C2 times V2 plus C3 times V3. For some C1, for some scalars, C1, C2, C3. Okay. So let's see what this means. So this is equivalent with so the first vector was 1, negative 2, 2 is C1 times V1 was oh my V1 was 1, 2, 3. So 1, 2, 3 plus C2 times I think that was 0, 1, 2 plus C3 times, and the last one I think it was negative 1, 0, and 1. Okay. So that is the linear combination of this. So let's do the computations. The computations are similar to the previous example. So this will be equivalent with 1, negative 2, 2. And here I'm going to write it. So this will be C1, 2C1, 3C1 plus 0, C2, 2C2 plus the last one is negative C3, 0, and C3. And by doing the operations, this will be equivalent with 1 and negative 2, 2. This is C1 minus C3, 2C1 plus C2. The last component is 3C1 plus 2C2 plus C3. Okay, so it's the same thing. And now equating all this, this will give us the following. This will be equivalent with the following system. The system will be similar to the previous one, but a little bit different. So it will be C1 minus C3 is 1. 2C1 plus C2 equals negative 2. 3C1 plus 2C2 plus C3 will be 2. You see, this column of free coefficients is changed. It's not 1, 1. Now it is 1, negative 2, and 2. All right, so this is a system, again, a system of linear equations, 3 variables. And if you want to write the augmented matrix of this, so the augmented matrix is given by the following. So let's write the matrix. This will be 1, 0, negative 1, 1, 2, 1, 0, negative 2, 3, 2, 1, 2. Okay. This is the augmented matrix. And we want to perform elementary transformations to this. So in other words, by this augmented matrix, the augmented matrix by elementary transformations, and I'll leave this to you as an exercise. So Gauss-Jordan elimination. So this is an exercise for you. The augmented row reduces to the following matrix. Let me write it here. Will be 1, 0, negative 1, 0, 0, 1, 2, 0, and the last one will be 0, 0, 0, 1. Well, what can you tell me? So this will be equivalent to this. What can you tell me about the solutions here? No solution. If you look at the last row, you see you will have that 0 equals 1. So there are no solutions. For the system S. That's it. In other words, now we're going back to our initial problem. This will answer our question, which was if we can write any vector as a linear combination of vectors v1, v2, and v3. Well, you see, I kept those 3 vectors, v1, v2, v3 from the previous example, and I just took another vector. Instead of 1, 1, 1, I took 1, negative 2, and 2, and there you go. So you see, you have seen examples of linear combinations of vectors that can be written as a linear combinations of other vectors, and now you have seen an example of a vector that cannot be a linear combination of vectors. Basically, we took the same vectors, 2 examples with the same vectors, v1, v2, and v3. Okay, I think this clears up the picture, I hope, for linear combinations of vectors. Do you have any questions so far? I think it's clear. So it's clear for everybody. Okay, that's good. Okay. Now I want to talk about something else. So the second thing, let me just a second. I want to write them in order. So the second thing I want to talk about is, so we talked about the first thing is linear combinations of vectors in a vector space. And now I want to talk about spanning sets in a vector space. So the second thing, spanning sets. In a vector space. Okay. Let's again, let's start with the definition. So the definition is the following. Let's consider a set. Let's say S is of vectors v1, v2, vk. Be a subset of a vector space V, of a vector space the set S is spanning V S is spanning set V when every vector, let's say in V, can be written as a linear combination, of vectors in S. In other words, if I pick a vector V in this vector space V, then V can be written as a linear combination of the vectors in S, which are V1, V2, and Vk. In such cases, it is said that S spans V. And we will see examples of vector space of a subset which will span the entire vector space. I want you to look at the definition a bit. Um, okay, and now let's see some examples. We want to see examples of sets that will span the entire vector space. And the first example that I have in mind, I will consider a set S, which will consist of these vectors: 1, 0, 0 in R3, 0, 1, 0, and 0, 0, 1. So this is the set. This set S spans the whole R3 because every vector, let's say U of components U1, U2, U3, in R3 can be written as a linear combination of vectors let's say these vectors of vectors, let's call them E1. I will denote them like this: 1, 0, 0. E2 is 0, 1, 0. E3 is 0, 0, 1. Well, is this true? Well, if you look at it, U is nothing else than just U1 times U1, 0, 0, plus U2 times 0, 1, 0, plus U3 times 0, 0, 1. You see, this is a linear combination of vectors E1, E2, and E3, and scalars U1, U2, and U3. So these guys are scalars. And there you go. So any vector, and you can go even in R4, R5, and even in Rn, you can do this. So the set of, we will call this the standard basis for, we'll get there for the vector space for Rn, for example. Let me give you another example of vectors. So another example, the set. So we want to show that the set, let's say S, which will consist of vectors, let's say 1, 2, 3, 0, 1, 2, and negative 2, 0, 1, spans the entire R3. Wow. You wouldn't believe it, right? That this is a non-trivial set. As you can see, the vectors there are not quite the vectors that we have seen previously. It's not like 1, 0, 0, 0, 1, 0, 0, 0, 1. These are just, if you look at them, just arbitrary. So we want to show that this set spans actually R3. So in other words, this means that any vector in R3 is a linear combination of the vectors in this set. So let's see. So consider U to be U1, U2, U3. Any vector in R3, right? And we need to find, we want to find scalars C1, C2, and C3 such that what? Such that U, which is U1, U2, U3, is C1 times the first vector, 1, 2, 3, plus C2 times 0, 1, 2, plus C3 times negative 2, 0, and 1. Okay. Now let's do the computations. I'm going to skip some of them. I'll leave it to you as an exercise. Some computations. I'm just going to write directly. So after some computations, you'll get the following system. You'll get what? You'll get that this is let's say C1 plus minus, so C1 minus 2C3 is U1, right? Then you'll have C1, 2C1 plus C2 equals U2. And the last one, you will have 3C1 plus C2 plus C3 equals U3. Okay. So what to do from here? So we need to solve this system, right? So how would you approach this system? You see those U1, U2, U3 there. We write it as a separate matrix, but but how would you suggest to write this as a, so okay, so the augmented matrix is given by, so let's write it, 1, 0, negative 2, U1, 2, 1, 0, U2, and then 3, 1, 1, and U3. And what to do from here? That is the question. Multiply by C1. Wait, I don't understand. So, Liliana, so you want to, So you want to multiply by C1, C2, C3? Which one you multiply? Who you? Anyway, the problem is that this guy, maybe you'll feel puzzled by this guy. Maybe this guy will bother you, but not so much. So you can just perform elementary transformations like um, in the previous case, and I'll leave it to you as an exercise so that I wouldn't lose too much time. So just do the same thing, Gauss-Jordan elimination. Elimination. Okay. Now, I want to talk about something, and that's something I want to talk about is linear. So we have seen, I want to talk about linear independence and linear dependence. So linear independence and linear dependence. Okay. So let's see, for a set of vectors, let's say S to be will consist of vectors v1, v2, vk. In a vector space, V, the vector equation C1 V1 plus C2 V2 plus all the way to CK times VK equals 0. So this vector equation here has the trivial solution C1 equals C2 equals all the way to CK equals 0. So if we have this equation, and this vector equation has only the trivial solution, then we can say that we have what we will call linear independence. But sometimes there are non-trivial solutions. So you see, we have seen vectors. There will be vectors for which their linear combination will give you 0, but those scalars are not 0, and we have seen such examples. And we will call those vectors linearly dependent. So we have seen an example. Let me give you an example. Let's consider the set S to be will consist of these vectors 1, 3, 1. Then I'll have 0, 1, 2. Then I'll have the third vector 1, 0, and -5. So this is V1, this is V2, and this is V3. One can check that, one can verify that V1, let's say, is 3V2 plus V3. So the vector equation C1 V1 plus C2 V2 plus C3 V3 equals 0 has a non-trivial solution. Has a non-trivial solution. what do I mean by non-trivial solution? I mean that it has a solution in which the coefficients are not zero. This means that in which the coefficients are not all zeros. In other words, in our case, these coefficients are C1 is 1, C2 is -3, and C3 is -1. See, so the coefficients are not zero. And now we can say the definition. So definition of linear independence. A set of vectors, let's say S of vectors v1, v2, vk, in a vector space, V is linearly independent when the vector equation C1v1 plus C2v2 plus CKVK equals 0 has only the trivial solution, has only the trivial solution. And when I say the trivial solution, I mean C1 equals C2 equals all the way to CK and equals 0. Okay, so that's the definition of linear independence. So you look at the vector equation, and then the conclusion you have to draw by looking at that vector equation is that the scalars must be all 0. And let's see examples of this. So let's see some examples. So examples, well, because I want to test linear independence. Let's take the set. The first example is, consider this following set. S to B will consist of this 1, 2, these two vectors, and 2, 4 in R2. So what do you think? Do you think this is linearly independent or linearly dependent? Well, what do you think? So let's look at the definition. So the question I want to ask here is S a set, okay, is S linearly independent? In other words, does this set of vectors obey the definition above? In other words, if we consider the vector equation C1 times 1, 2, plus C2 times 2, 4, to be 0, right? To be 0, 0. Does it follow that C1 and C2 are 0? What do you think? That is the question. Does it follow that C1, C2 are both 0? What do you think? This is the question I want to answer. Does it? Are you somebody? Liliana said yes. Let's see. So who is this guy? This guy is what? C1 plus 2C2 equals 0, and we get the following system. And 2C1 plus 4C2 equals 0. In other words, the second equation is just is the first equation multiplied by 2. So the only thing we care about is C1 plus 2C2 equals 0. So C1 is negative 2C2. Does it follow that C1 and C2 are always 0? You see, so wait, is linearly independent or linearly dependent? That is the question. You said yes, but yes is to you multiply. Yes, indeed. So if you multiply negative 2, you'll get 0, 0. You see, these constants here, C1 and C2, are not 0. And you have seen that we can find a linear combination of which will give you 0, but the constants are not 0. So what does this mean? Is the set S linearly independent or linearly dependent? So S is what? Is what? Look at the definition above. Exactly, dependent. Is linearly dependent. Because we have doesn't obey the definition above. So if it obeys the definition above, it's the set is linearly independent. If it does not, then the set is linearly dependent. Let me give you another example. What about this set? Let's take this set. Let me change the set T of vectors. Let's take the origin in R2, and the second one is 1, 2 in R2. The question is T linear independent? Linearly independent? What do you think? Well, in this case, you have, what do you have? It's, again, indeed, linear, like Liliana says, the answer is no. It's linearly dependent. T is linearly dependent. Right? So what does this mean? This means that I can write vectors. Let's say I can find constants. Let's say 1 times 0, 0 plus 0 times 1, 2 to be 0, 0. As you can see, this guy is 0, But this guy is not 0. So these are the scalars. So all of them must be equal to 0. So indeed, this is not um, um, linearly dependent. And now I want to test linear independence. And I think I'm going to, after this example, I'm going to maybe just say a few words so how to give you a general strategy of testing linear independence. And then I'll tell you to examine some of my other examples from the notes. And probably I'm going to stop. Well, the example that I want to cover, another example, is we want to test, so testing a linear independence. In other words, we want to see when a set of vectors is linearly independent or linearly dependent. So the question says the following: determine whether the set of vectors in R3 is linearly independent or linearly dependent. And the set is given by S is V1, V2, V3 is 1, 2, 3. The second vector is 0, 1, 2. And the last one is negative 2, 0, 1. So that is the question we want to answer. So to test linear independence, we need to form the vector equation. So the vector equation, in our case, will be, so the vector equation is given by, so let's take C1 of V1 plus C2 V2 plus C3 V3 equals 0. So that's the vector equation. And this will be equivalent with C1 times 1, 2, 3 plus C2 times 0, 1, 2 plus C3 times negative 2, 0, 1. And we have to set it is equal to 0. So in our case, it will be the vector 0, 0, 0, the 0 vector in R3. And after doing all these computations and everything, we'll end up with the following system S. And this time the system will have something in particular. So the system is C1 minus 2C3 equals 0. 2C1 plus C2 equals 0. And 3C1 plus 2C2 plus C3 equals 0. So this is what we call, as you can see, this column here is made of zeros. This is what we call homogeneous linear system or homogeneous system of linear equations. You can see I have all zeros here. Well, you can do the same thing. You can write the augmented matrix. The augmented matrix is given by the following. So let's write it. Let's denote it by A. This time let me write it. So it will be 1, 0, negative 2, 0, 2, 1, 0, 0, 3, 2, 1, 0. Okay, so this is the augmented matrix. And then at some point, I will leave it to you as an exercise by doing Gauss-Jordan elimination. So again, I'll leave it to you as an exercise. This matrix will be equivalent with the following matrix. So it will be 1, 0, 0, 0. You'll be surprised. 0, 1, 0, 0. 0, 0, 1, 0. And of course, I have to obtain, in the end, I have to obtain this matrix because this will force me to conclude that C1 equals C2 equals C3, and this is 0. So by concluding this will imply that my set is what? Is linearly independent or linearly dependent? Indeed, so S is linearly independent. That's it. And this is how you test it. You see, at the end of the day, you have to solve a system of linear equations. Now I'm just gonna give you. So how do we test linear independence? So testing linear independence. And I think, or maybe I'm just going to give you one more example. I think I'm going to stop. So let S be of a set which will consist of vectors v1, v2, vk. So this be the set of vectors in a vector space V to determine whether S is linearly independent or linearly dependent use the following steps. Steps below. Okay. 1. Form the vector equation C1 V1 plus C2 V2 plus CK VK equals 0. So we're going to form this vector equation. And after we form this and write a system of linear equations in the variables C1, C2, CK, right? So this is what we did. Then the second step is determine whether the system has unique solution. This is very important. And then the last one, if the system of linear equations from step 1 has only the trivial solution So when I mean the trivial solution, this means that C1 equals C2 equals all the way to CK equals 0. Then S is linearly independent. Independent. Otherwise, S is linearly dependent. Linearly dependent. That's how we test linearly independence. That's what we did so far. And now, let me give you another example, and I think I will be done here. In fact, I will leave this example to you as an exercise. So example, so this is an exercise. It's just, it goes along the lines of previous examples. So determine whether the set of vectors and I'm going to consider now a set in the vector space of 2 by 2 real matrices is linearly independent or linearly dependent. And the set is given by the following. I'm going to denote this by S. By the way, don't make any confusion between the set S and the system S. They are two different things. Maybe I shouldn't have written the system with S, but you understand S in parentheses is the system. S without anything is just the set. So the set is 2, 1, 0, 1. So this is my first vector, which is a matrix. This is 3, 0, 2, 1. And the last one is 1, 0, 2, 0. So this is my vector. So this is V1, this is V2, and this is V3, right? So in other words, what do you need to do? Well, you're just gonna do the same thing as described here. How? So we're gonna test the linear independence. In other words, you're gonna do the following. You're gonna form the vector equation. Then you'll write the system of linear equations in the variables C1, C3 in our case. By the way, the null vector here in this case, it will be the matrix, the 2 by 2 matrix with the 0 entries. And then you're just going to play around. And you'll have a system, and you have to see if that system has a trivial solution or not. If it has a trivial solution, then you will conclude that the set consisting of these three vectors is linearly independent. If it doesn't have the trivial solution, then you will say that the system is linearly dependent, and that's the story. Okay, I'm going to stop here. Thank you very much for attendance. Let me stop the recording.